Hi there, and welcome to part 9 of the synthesizer tutorial, and in this video we're going to look at note triggering and portamento. Synthesizers generally play in one of two modes, so you can have monophonic mode, which would typically be a bass sound. We don't want more than one note sounding at once because it would sound really thick and muddy and terrible. And polyphonic mode, which you would typically be looking at a pad sound where you would want to play chords. Okay, let's look at monophonic mode first, then polyphonic mode, and then we'll have a look at portamento. Okay, so here we have a keyboard, and the keyboard will play as many notes as you like, but this is feeding into a monophonic instrument. So how does a monophonic instrument react to having multiple notes played? Obviously, if I play that note will sound. If I play that note, then that note will sound. But what happens if I do that? Well, we have three modes, which is what I've implemented. You could do all sorts of things, and at some point we may see what we can come up with. But what I call mono mode is that note will sound, that note will sound, that note will sound, and the note will stop when this last note is released. The next mode I've known as multi-mode, in which it will play that note, that note, that note, but then if I release that note it will re-trigger that note, and then release that note it will re-trigger that note. This enables me to pretend to the world I can play the keyboard very fast by doing that when it's actually playing that, which I can't do anything like as fast. And the final mode is Autoglide, which the triggering and the portamento are linked. So the first note I play, it triggers the envelopes, and then subsequent notes I play, it glides to those notes without re-triggering the envelopes. This gives an effect not unlike you would imagine playing a trombone, where the first note you start it goes bong, and then it bong, as you move the slide up. Okay, so we'll look at each of those three in turn. Okay, so I've set up a series of notes to demonstrate how each of the monophonic modes works, and here they are. Okay, the horizontal axis is time, and each one's color coded, and the number at the left is the MIDI note for each note, but this is not important for the purposes of this demonstration, and I'm proposing to use this diagram to demonstrate how each of the modes works, rather than showing you code and say this bit of code does that and that bit of code does that, because it's easier to understand. If it's a picture, always draw a picture. Easiest way to understand things, and the code will be available to download if you actually want to look at what's going on, and contact me if you have any queries regarding the code. So firstly, here is our set of notes, and let's first play them polyphonically, just so we know what notes there are and how they sound. So here we go. Okay, so now let's move on and look at what I call mono mode. Okay, so here the coloured lines represent the keys that are held down on the keyboard, and in polyphonic mode those notes are just played. as they're held down. But here the black line represents the pitch of the voice, and the diamonds represent when the envelopes are started, so a new note is played. And because we also want to know what the portamento is doing, I've represented portamento by just a straight line going from the old pitch to the new pitch. So here, the very first note, there's no portamento because we don't know where to portamento from. And after that we portamento to every note, and every note we play we treat as a new note. The envelopes are started, and we get to the top here, the turquoise note, and we get a note off for the note that's actually sounding, so it just turns the note off there and ignores all the other note off messages, should I say. And similarly here, well, it portamentos from the pitch of the last note played right down to this new note down here, and again each new note on it plays that note, and it stops when it gets the note off the turquoise note here. And similarly in the final section, here it stops because it's got the note off to the blue note, and starts again here and plays the turquoise note. So shall we see what that sounds like? And looking at the little WAV file, you can see here the right hand channel. I've actually modified the code temporarily to display the pitch. This is the actual pitch we're seeing, starting there where the first note starts. So let's play this. Okay, so now let's look at multi-mode. Again, we have the notes, the actual keys played are the colours. We have the actual pitch of our monophonic voice in black, and the diamonds represent the points the envelopes are started. However, here we have the addition of a key stack, which is my name for it, which holds a record of the notes that are currently being held down. So here the red note is played, and here the green note is played, so the green and the red are stored, with the newest at the bottom. Again, that's just my implementation. Here the blue, the red, the green and the red notes are played, and here the turquoise, the blue, the green, the red are played. And as for the monophonic mode, when a new key is played, that note is always started. So same as monophonic mode up to here. The difference starts here where we release the key for the turquoise note. So you can see that has gone out of the key stack, and we know we've had a note off message for the note that was sounding. So in multi-mode we say, we need to start another note if there is a note in the key stack. In this case it's the blue note, and you can see here in the key stack I've outlined the blue note in a thick outline, and that is the note that is now played. And here the blue note is released, so we say, that's the note we're playing. So have we got another note to play? Yes, we've got the green and the red. The green is at the bottom, so that is the one we are going to play. And again here the green note is released, and we say, do we have a note on the key stack? Yes, the red note, so we will start the red note. And here the red note's released, the key stack's empty, so that's it, we stop playing a note. And if we go here to the second set of notes, the last note played is the last note released, so that sounds exactly the same as it does for the mono mode, because when the turquoise note is released, the key stack's empty. And finally, yes, here the blue note's released, so we go take the green one off the key stack, and then the turquoise is played and the turquoise is released, and we again go back to the green note on the key stack because it's still the bottom of the key stack. So shall we see how that one sounds? And finally to Autoglide. This is designed to sort of mimic an instrument, shall we say a trombone, where the player, while not playing a note, would set the slide for the next note. So the first note when he starts playing is at that note's pitch. And then if he continues to play notes while continuing to blow into the instrument, he will glide between the notes as he's moving the slide. I'll discuss this more in a minute when we come to talk about portamento. So here, when the first key is depressed, the envelopes are triggered. And then, while at least one key is held, the pitch might change, but the envelopes will not re-trigger. And, well, this is my implementation, but here we have the note, the key stack, which works exactly the same as I've just described for the multi-mode. But here you can see, as we portamento to new notes, we do not re-trigger the envelopes until here we get to the end, and then we've got no key pressed, and then when we press a key again, it re-triggers the envelopes. And similarly here. So, shall we see what that sounds like? Okay, and that is a very common and very good effect on monophonic synthesizers. So now let us talk about portamento. Okay, so let's have a think about what we're doing with portamento. Now, acoustic instruments, a good number, can play any pitch. For instance, the voice. And for example the trombone should I say, and they can then continuously vary their pitch between one note and another. So let's look at the trombone as an example. Now, I don't have a trombone and I couldn't play it if I did have one, so we are going to consider air trombone. So imagine this is my slide, so if I am going between two notes, my slide will start stationary, will accelerate up to speed, and when I get to the new note, if I was a good trombone player, I would decelerate the slide and stop just at the right pitch for the new note. Okay, remember that. Now, in the days of analog synthesizers using gate CV to control their voices, this was the circuit that tended to be used because it's very simple to implement, where the variable resistor here gives you the portamento time, and yeah, and there's just that and a capacitor, and that will give you an exponential curve, and that is what tends to get implemented in digital synthesizers as well. But I don't think this sounds too good for the reasons I'll give you now. Here are some notes played with portamento between them. Now again, in the second channel I'm displaying the voice pitch, so we can see here our exponential portamento, and you can see at the start of the new note here the pitch suddenly starts changing towards the new pitch. And going back to our trombone, that would be as if the trombone player could get the slide moving from stationary to full speed instantly, which of course he can't do. And also at the end here you can see it's approaching the new pitch, but never quite getting there. I mean, it does eventually, but it just sounds strange and slow, whereas a real musician would actually get to the pitch in a fixed time. So shall we play these? And now I think it sort of feels jerky at the start and painfully slow towards the end. I'll let you make your own mind up. So in my software synthesizer, my VSTI plugin, the Pulsar, I address this problem. And by the way, I'm going to get back and update the Pulsar at some point, so look out for that. So instead of the exponential decay, I used a cosine wave. And here we have a cosine wave, and I use from there to there. So it starts with the slope at 0, goes up to a maximum slope, and the slope there is 0. And so instead of 1 we have the start pitch, and instead of -1 we have the finish pitch. So when we play a new note we have to work out the scale, and we have to work out the increment through the wave, and the wave is stored in a table and interpolated in a similar manner to lots of things in previous tutorials, so I'm not going to go into that now or go through the code with you. So that produces the following result. Now I think that sounds a whole lot more natural, and works well, and is, I say, what's in the Pulsar, but is a bit clunky to set up. So while working on these tutorials I had a bright idea for a third option. And the third option, which I've implemented here, is to use the state variable filter algorithm that we use for our main filter and for our smoothing, and that's just implemented here, and that's nice and quickly. And incidentally, you can see above how easy the exponential is to implement, and that sounds like this. Okay, and here they are, each in turn, so you can compare them directly. Okay, and here I have plotted the portamento between note 68 and note 52, those are MIDI note numbers, for the three types, just so you can have a visual comparison as well. And as you can see,
when it comes to starting, yeah, the cosine is the smoothest start, and the exponential is, as we've discussed, a sudden start. And at the end, the cosine reaches its destination in a nice defined time, and as we can see here, the filter sort of drifts on a bit, but it's okay, and you see here the exponential is getting there ever so slowly. So that's that for portamento. So I think I still like the cosine best, but it's up if you're designing your synthesizer. You choose what you think sounds best for the application you're designing it for. I'm just really here trying to say, hey, you can think about portamento. You don't just have to do the exponential version just because every other synthesizer has it on.
Okay, let's talk about polyphony. Now, up to now we've discussed monophonic instruments. Use a trombone as an example, which has one voice, one sound generating apparatus, which is basically a tube. So at the other end of the scale we have, I guess, something like a piano, which has 88 voices or sound generators, which are a set of tuned strings in the case of a piano, and each one of these is dedicated to a specific note and only plays that note. And you can play on a piano as many notes as possible. If you put the sustain pedal down and run your handle on the keyboard, you can play them all at once, which leaves a sort of category in the middle, which guitar is the best example, I guess, where you have 6 voices, 6 sound generators, each of which can have their pitch set independently. And at this point we are going to sort of overlook that and move on with polyphony in the mode of a piano. So it would take up a lot of processing time to have a synthesizer with 88 voices, sound generators. So we must somehow assign a smaller number of voices to all the notes we can possibly play. Now, in the Pulsar I did actually have 88 or however many it was voices, and actually turned them off when they weren't making any sound. So the polyphony was as much as you wanted, given how much CPU power you had to play with. This technique isn't really applicable to a hardware synth where you have a fixed number of voices you can create from your processor. So we need to think of something different. Now, I'd just like to mention in passing the case of a multi-timbral instrument, which we're not going to go into here. But specifically, General MIDI will dynamically allocate its available voices across different parts. So you can get the situation where you play a piano note and the crash cymbal suddenly cuts out, which stands out like a sore thumb. So I have always implemented it where for each part, if we're talking about a multi-timbral synthesizer, a multi-part synthesizer, each part you set the number of voices, the polyphony, that is available to that part. And if there are more notes played than you have voices for that part, then you only have to steal voices from that part. So how do we do this? How do we allocate a fixed number of voices against potentially a very large number of notes played? Well, when a new note is played, that note must sound, so we must take a voice from an existing note to play that note. And the question then is, which existing note do we cut off and take its voice from it? Well, the simplest way of doing this is simply to go around and find the note that is quietest, i.e. the amplitude envelope is at its least value, and steal that one. But that can cause problems if you have an organ type sound with a high sustain level and a very quick decay, because they can all be at the same level, so you might end up just stealing the last one played. So what we do is we keep track of the time that each voice was started, and if there is at least one voice in the release phase, we take the oldest one of those, and otherwise we take the oldest one in the sustain phase, or the one that's actually playing. Again, I don't propose to go through any code to show you how this works. Actually, instead use, as I did before, use some diagrams. So, shall we see how we're going to do this?
Alright, so we're going to look at two examples to demonstrate how this works, and in the first one we're going to play 8 notes, which is C major chord, starting at MIDI note number 48 and finishing at MIDI note 76, and then we're going to hold them for a couple of beats and then release them all. So the filled in dot is the note on, the open circle is the note off. The voices are colour coded, so there's 8 voices here, so we know we can play all our notes, so there's 8 colours, and the dashed line here is the release phase, and if the release value is set up high in envelope 1, there might be sound generated by the voice quite a long way along here. So if we run that scenario, okay, so that's what it looks like on a little test sequencer format. Okay, so if we run that, it's telling us what it's doing. And that's the result, and that sounds like this. Okay, so all the notes playing, because we're playing 8 notes and we've got 8 voices. So now let us consider the situation where we play the same notes and we've only got 4 voices. And here we are. So it plays the first 4 notes fine, but when it gets to the 5th note here, it's run out of voices, so it steals the voice from note 48, the red voice, and you can see here the black dashed line, the key is still pressed, the player is still expecting the note to sound, but it's gone, it's been used here. And that one is taken because it's the oldest voice that's being used. And similarly, note 67 steals the green voice, note 72 steals the blue voice, and note 76 steals the turquoise voice. And that sounds like this. And you can hear that the bottom 4 notes vanish, turn off, because we've had to steal their voices. And just by way of comparison, we'll play them both one after each other. 8 note polyphony, and then 4 note polyphony. Okay, so let's consider a slightly more complex case. Again here we've got 8 notes and 8 voices, so no voice is going to be stolen to play another note. So we start with 48, then play 52, 55, 60, but then we release 55 and then release 62, and then play 64, 67, 72 and 76, and pause for a couple of beats and release the remaining notes. So with 8 notes that sounds with 8 voices that sounds like this. So now let's see what happens when we only have 4 voices available. So we play our first 4 notes and they start nicely, and we release the key for 55 and then 52, and everything is still fine, but then we play 64. Now we have 4 voices in use, so we're going to have to steal one. Well, we steal the one that was released first, so is longest in its release phase here, which is the blue one. So 64, we take the blue note, and when we come to play note 67, we see the green voice is on its release phase, whereas the red and the turquoise are still being played, so we will take the green voice. And we play note 72, and at this point all voices are being used by notes played, so the red one is by far the oldest, so we take that. And finally note 76, we take the turquoise voice. So in this case we can see the red and the turquoise notes are still being held here. The player expects them to be sounding, but we've stolen the voices as indicated by these dashed black lines. So shall we see what that sounds like? Okay, and again I've done them one after the other so we can compare them directly. So the 8-note polyphonic version followed by the 4-note polyphonic version. Okay, it doesn't actually sound too bad, does it? So I think that algorithm works quite nicely.
Okay, that's it for note triggering, polyphony and portamento. As usual, I'm sure YouTube will mangle up the audio examples, so all the WAV files are available to download should you wish to listen to them as they should be heard. There'll be a link in the description. Similarly, a copy of all the development code that I've used to generate the examples will be available via a link in the description. So next time we will be looking at how playing a new note affects the LFOs and the oscillators. You might say, does it at all? Well, I shall be, I hope, convincing you that it does, and we need to address how it affects the oscillators and the LFOs. So until then, it's goodbye from Triplicate, home of interesting electronics. Goodbye.